We are about to the fourth lesson, not the review lesson, I suppose. Um, for review, video number 4, circular motion. All right, so usually we refer to it as uniform circular motion. And when we say uniform, it means things have to be the same. Just like when people wear uniforms at their job, they have to look the same. Uniform means constant speed and constant r, constant distance. So you're going in a circular path, right? This, and your speed is going to change. Say these were different points that you're moving around. You're going around, and this is just some representing something that's moving, right? Point 1, point 2, point 3, point 4. Since the speed is not changing, this velocity vector, which remember is tangent, and that's why we call it the tangential velocity vector. We usually use v. So will AP Physics. They'll use a exam. They'll use a VT vector. Just remembering, if you have a curve and someone says draw the tangent line at that point, it's a line that touches and it crosses through that point, but does not intersect the circle. It doesn't go through. Can't intersect the circle. That's what tangent means. So that's why we call it the tangential velocity vector, which, by the way, is changing in direction, right? Because now the tangential velocity is actually to the left. Could call that west. Now the tangential velocity is to the south. Now the tangential velocity is to the east, just because the direction of motion is changing. Circle for sure, right? So even though the speed is not changing, we have to recognize a massive part of this unit is the idea that it's still accelerating, and that can be confusing at first. This is a review, so hopefully you recall. The reason that we still say this is accelerating is not because it's changing its speed, it's because its velocity is changing. Remember that speed is just meters per second speed. Velocity is your speed plus your direction. It's a vector. Speed is just a scalar. So if we know already from prior lessons, early before we move this forward, that acceleration is defined as the rate of change of the velocity vector. Technically, how rapidly the velocity vector changes. Magnitude, which is in speed, the length of the vector is the magnitude of the velocity vector. We call it speed. So the rate of change would technically depend on two things, because two things can change about a vector. It could be the length of the vector is changing, the speed could be changing, or the speed is not changing, which is definitely the case here because we said it's constant speed, but the direction is in fact changing. And if only the direction of these vectors are changing, which is why our velocity vectors are all the same length. If the direction is changing, then this is really in reference to the rate at which the direction is changing, the direction of the velocity vector. And definition, then, that means we must be accelerating. There must be some sort of acceleration. And we call that the centripetal acceleration. Centripetal means center seeking. I think it's Latin. So a centripetal acceleration, just like a centripetal vector, is pointing towards the center of the circle. It's a center seeking quantity. Which direction is the centripetal acceleration? Well, very quickly, if we looked at two vectors, let's say one here, a moment later you're going here at v2, recognizing that I'm trying to draw those equal length to indicate that you haven't really sped up at all down, you're just changing your direction, you're just navigating this turn. If we wanted to look at, well, what does delta v actually look like? Delta 2 minus v1. Right? So a delta v, remember, is actually a vector subtraction, right? So if we want to do v2 minus v1, need this side of the circle anymore. We could do v1. This is v. I just moved it over, and v1. I guess v1 is a little not quite in the right direction. v1 looked more like I guess. Oops. There we go. So this is like our v2. So the resultant would go from here to here. Right? And that vector right there, we would say is v1 plus v2. But we're not doing v plus v2. We're doing we're not doing v2 plus v1. I guess it's the same as saying v1 plus v2. we're actually doing v2 minus v1. So if this one was, again, v2 plus v1, then I would just have to switch the direction of v1 to make it a minus v1. Minus v1 would actually come this way. This would now be minus v1. And if this first vector that I've drawn is v2, it's horribly, I'm really sorry for that. This one was v2, and this is now negative v1, then the resultant now goes to right from here. It goes from the beginning of the first vector to the last, right? So this is actually representing delta v. If we now take that vector, drag it over to where we were, which way would it be pointing? The delta v is actually in the direction pointing straight towards the center, the delta v vector. That means in between those 2 points as you move along, the change in direction vector actually points straight towards the center, right? And that means since acceleration is proportional to delta v over delta t, right? And a is actually a vector, is in the same direction of delta v. That means our centripetal acceleration must be in the same direction of delta v. So if delta v is actually pointing towards the center, then acceleration vector must be pointing towards the center. And we now call that, again, a centripetal acceleration. It's not speed is due to a change in direction. Now we would, review, well, what does the centripetal acceleration depend on, other than the fact that it's always pointing towards the center, right? Always. Centripetal acceleration vectors would be pointing, as this thing moved around its path, towards the center. Towards the center. They're all pointing towards the center. The center-seeking force, centripetal acceleration. Now we'd wonder, well, what does it depend on? Centripetal acceleration, thanks to Newton, who figured out this using some geometry and kind of some vector stuff. You could always watch it on YouTube, whatever. It takes about, 7 or 8, 9 minutes to show that this not only is a vector that points in the direction towards the center, the centripetal acceleration, but it's also in an amount equal to v squared over r. So this is our centripetal acceleration, right? Worth noting that the centripetal acceleration is inversely proportional to r, right? So that means something that's moving around a small circle like this, round and round it goes, compared to something that's going around a larger circle. Let's assume they're going the same speed. So let's say that the speed here is, I don't know, whatever, 10 meters per second. And then this thing also, little hoop at 10 meters per second. They're both going around their hoops at the same speed. Which one has the greatest acceleration? Well, the little guy, right? The little one has a very rapidly changing direction because it's a very tight path. And notice that there's an inverse relationship to indicate that. When r is small, the centripetal acceleration is high. Or when r is large, centripetal acceleration would be smaller, assuming they have the same speed, right? However, the centripetal acceleration is all proportional to how fast you're moving around the circle, which makes sense, because could you technically still achieve a very rapid rate of change of direction, even on the bigger circle? Sure. Even though it's a big circle and the geometry of it should reduce the centripetal acceleration, since it's just a big circle, it takes a long time for you to get around it. Someone might say, just go way faster. Just go super lightning speed fast, and the direction of that velocity vector will still change super quickly, right? That makes sense. So there should be some sort of proportion between v and a, right? Because ac, again, is the rate at which your direction changes, your velocity, the direction of your velocity vector. So it makes sense there had to be some sort of v, and it makes sense there in the numerator, and it makes sense there should have needed to be some r in the denominator, just from logical thinking, that more speed should increase the centripetal acceleration, while less radius should actually increase the centripetal acceleration, which is why the radius would have to be in the denominator and the velocity would have to be in the numerator. Right? No one would know that it was squared until someone like Newton figured that out. But anyways, combining those, this is your centripetal acceleration. Right, so if they give you the speed, they give you the r, you can technically model or calculate or compute the rate at which the direction is changing as something goes around, knowing also that it's always in the direction pointing towards the center and knowing that it's a vector. Next, we talk about the centripetal force, right? Newton said, well, F is always equal to an m times an a. And here, my centripetal acceleration is, which is an acceleration, is v squared over r. So that whatever force is necessary to cause this centripetal, right? Because now we're talking about forces. Does it require a force to cause the direction of something that's moving to change? Like if you want something not necessarily to speed up, you just want it to start turning, do you have to apply a force to it to make it change its direction? Yeah. And he said, yeah, that would be called centripetal force. And it's equal to mv squared over r, right? And then you'd think, well, what is the direction of it? What is the direction of it? Well, remember that F and A are always in the same direction, always, at least net force. Centripetal force is like net force, and I'll talk about that in a second. But if we already knew that the centripetal acceleration would be a vector pointing in, then at that same point, the centripetal force would be a vector pointing in. So the centripetal force, again, is also always a force pointing in. It's the force needed to make the direction change. How much force is required? Well, depends on how much mass it is. If it's a heavy truck, it's going to take a lot more force to make it change the direction as it goes around the rotary. How much force is needed depends on how fast the truck's going, and how much force, that inward force that truck needs to experience, depends on how wide the rotary is, right? It's a combination of those factors. So that's the idea of centripetal force. It's a force, again, that I want you to know it's just a generic word, centripetal. It's as generic as saying kid, and then saying, well, I have an older kid, and his name is Caleb. And I'm saying this because what we sometimes see as teachers when we look at students' work is we would see something like this, that we would say, at this point right here, draw a free body diagram for the object. And we see somebody draw, I don't know, let's just say it was a rope or something. Let's say, and I'm going to do that problem in a moment. Let's just say it's a ball going around and around this loop. If that were the case, then there's a tension pulling the ball inward, providing the centripetal force, because it's a force. This is, again, a free body diagram for when the ball is here, going around. And then we see the student also put another vector and go FC. And we have to say, oh no, those are the same. Those aren't two vectors. Those aren't two quantities or two forces. We would say that the tension force is a centripetal force, just like I would say I have a kid. Centripetal force is like just very, very general. Centripetal force like kid. And then I'd say, but I have a kid named Caleb, right? I wouldn't say I have one after I say that. So, okay, list down your kids you have, and right, first kid I have is kid. Second kid I have is Caleb. Say, what are you talking about? That makes sense. He's one kid. He's one kid. His name is Caleb, right? This is the same idea. The tension force is the centripetal force. Centripetal force is just a placeholder. It's just a placeholder for whatever the problem is. And then once you're referencing the problem and you recognize what that inward force is, you take away centripetal force and you put whatever it is. So in this case, you would erase that, right? You wouldn't want that. It would just be the tension force. So that's an important thing to recognize. Always pointing towards the center. Same thing with the centripetal force that it's producing. Okay, now let's look at an example. Before I look at the example, is there anything else I would say about this? I guess there's something to say about this. Just in general, if you are looking at something that's going around a circle, when we see some force, like let's just say it's the tension again, and this was like a rope whipping a ball around. This is some tension in the rope. If the ball is going round and round, and you have the tension right here, and then you have the tension, always pointing in. As I said, actually, was I going to say the horizontal or the vertical example of what I was going to say? Yeah, it doesn't really matter. So all I wanted to point out is these would all be considered positive forces. Any force that's towards the center, because just remember, like when we're pushing blocks around, we say to the right is plus and to the left is minus. You have to be able to distinguish direction with a sign, a mathematical sign. Reminding you that there's the same thing here. For circular motion, any outward forces are considered negative forces, if there are some. Usually most of your problems are not, but there are some. Actually, no, take that back to them. And these are negative forces. in any inward forces or positive forces, because eventually you have to add them up, because the centripetal force is actually the net force. It's worth pointing that out. When we say the centripetal force, we're referring to the net amount of force, the unbalanced amount of force. So when we say that the centripetal force for something going in a circle has to be equal to mv squared over r, what we mean is that the net, if there's more than one force, like let's just say the object's all the way on the right in my image, and there's a tension pulling in, and then there's, I don't know, me pulling out, and there's two forces. And someone said, what is the net of those? I'd say, well, F net is, Ft is plus, so because it's towards the center, minus me, because I'm pulling whatever, minus the tension or the force from me, right? That would be the, that net is how much extra there is to the left, right? If this was 10 newtons and this one was 3 newtons, then the net force is 7 newtons pointing which way? Towards the center, right? What do we call that net force? We call it the centripetal force. At least when we set it equal to mv squared over r, I should say, we're referring to this as being, F net is taking now this new notation FC. So as soon as you set F equal to mv squared over r, we're assuming that references the net force. Which direction does the net force have to always point for something that's going in a circle? Towards the center. So if it's going around and they said draw a diagram and label F net diagram, it has to be. If it's going around a circle speed and a constant radius, then the net force has to be pointing towards the center. Even if there's some outward forces and other forces, the overall net force has to be pointing towards the center. Net force have to be equal to mv squared over r. Some pluses and some minuses, just like I just said here. And I said that the net force was 7 in this example. 10, 3 out, the net force is 7. That means m speed it has going around the circle divided by the radius of the circle would have to come out as 7. If that makes sense. The net force has to be pointing towards the center of the circle in an amount equal to mv squared over r. And as long as that's true, then the thing will continue moving at a constant speed around and around that circle at a constant distance, called uniform scalar motion. All right. Now we're going to look at two common examples. We're going to start with the rope and the ball. So imagine we have, I don't know, some post or something like that. We have a rope, and we have a bowling ball. And this ball is being zipped around a giant circle. And this is the floor. This is the floor here. What's causing that, that flip for us, if it's around our head, it'd be our wrist. Our wrist would be doing that. Like what's actually causing in the middle, causing, who knows? I don't know. Some machine is created that makes this happen, let's just say. If someone said draw a free body diagram for this, again, this is going around circles. Someone said draw a free body diagram for it on the left. You have to recognize that mg and Fn are still canceling. Those are still balanced forces. Yes, it's true that the overall net force on this object has to be towards the center, which we call the net force, or the centripetal, the sum of the the addition of all forces either in or out, which we're going to call the centripetal force. I know that can be a little bit confusing. I'm sorry for that. Sometimes people would just say, let's just say there was, I don't know, gravity pulling it in, pulling it in, and someone said, how many centripetal forces do you see? I'd actually say 2, because to me, a centripetal force is any force pointing towards the center. And says, but if you see 2, you're sitting there writing this, then like, how do you put both of those in for this? Where it gets a little weird. So I'm sorry, but that's just how we are as teachers. I like, a lot of textbooks actually show the sum of the forces that are radial, some of the radial forces. And they ended up saying, let's just call that the centripetal. Radial forces are any forces that are along this dotted line, along the radius, right? Because if that was my circle here that I'm showing, the radius would go right? So any forces that are to the right of that dotted line or to the left along that dotted line, we call radial forces, where ones are minus and where ones are plus. And this means add up all the radial forces and the net force called the centripetal force. I know, that's weird, right? The net force called, I know, there's 2 centripetal that will still refer to the net. I mean, they don't usually say the net centripetal force. I wish they did, but they don't. Textbooks actually just say the sum of all those called the net force, which we're going to call the centripetal force. It really should be the sum of, the net centripetal forces. So I'm sorry that that's the way it is. And they call that FC. So problem, although the net force, I'm going to go ahead and say the centripetal force on this is unbalanced and it's to the right, and that would come from the rope. The rope is technically applying a tension towards the center as this thing whips around, at least when it's on the left side of the circle. So although the overall system has unbalanced forces, it has to be the case with an extra amount of net unbalanced force towards the center. Pointing out Fn and mg are not sideways forces. I've seen that many times, right? Sideways things don't affect vertical things don't affect sideways things in all cases. So the fact that this thing is moving around this horizontal circle has a horizontal force on it from the rope has no effect on Fn or Fg. When you stop the whole system, the ball just sits still, Fn is still equal to mg. What I'm whipping around really fast, Fn is still equal to mg. That's not affected by anything, right? So this would be free body diagram, right? And if someone said, for example, what is the tension in this rope? Maybe they give you some information or use laws to model this. Or we would say, if you want to just write F net, that makes it easier, equals mv squared over r. Might make it easier. And you would just say, all right, I've got how many forces towards the center? Just one. It's plus because towards the center is plus. Any forces to the left, like away? No, there's none. That the tension in the rope must be equal to mv squared over r. Like that, totally. That's totally correct. Now, if they asked, what is the centripetal acceleration? It would just be the v squared over r, right? R would be the length of the rope. Recognize that that's the length of the rope. So you have, that's how you would model it. The tension would just be equal. Let me point out, they probably wouldn't just give you the information to make it a plug and chug. They might say, the period is, 2.3 seconds. And the radius of this, they wouldn't even say the radius, they'd let you make that connection. And the length of the rope is 5 meters. You'd have to recognize that the length of the rope, right? And then you're coming upon this and thinking, I don't know what V is. How do I get V? They only gave me period, which is the time to go around once. Well, you have to remember V equals 2 pi r over t, right? That's your speed equals distance over time, because that's a constant speed motion formula. Just the distance is now the distance all the way around, 2 pi r, the circumference. Capital T is now the period, the time to get all the way around, right? So if they've given you T, like I've described, check, and they've given you can actually plug those L, which is put in for R. You could just do 2 pi times, in this case, 5 divided by 2.3 and get V. Or you can model it by just lifting 2 pi R over T straight in for V. If that's what they wanted you to do, right? So just reminding you on that. They probably would just give you this. They'd give you something like that and have you figure it out. Is there to say about this? Well, I mean, if it increases its speed, right? If this thing starts spinning faster, what would happen to the tension? Well, look at the model. What is the model suggesting? The model at the very bottom of the screen is suggesting that the tension in the rope should be proportional to the speed squared. If this thing goes around faster and faster, R is not changing, M's not changing, speed is increasing, then the tension, should have some sort of parabolic increase with V. It'll increase, right? Twice as much speed, 2 squared, 4 times as much tension, right? Or if we made the, took the ball off, and we didn't change how it was moving around, but in a second trial we put a heavier ball, used a heavier bowling ball, and then we repeat it all the same distance, same rotational speed, everything's the same. Well, we'd see from below the tension force is proportional to M here, right? Twice as much mass. Oh, twice as much mass in the bowling ball. Twice as much tension force. No, nothing else changes, right? So that's those ideas there. Is there anything to say about this? I guess a little bit. They could fold rotation into this, and I will point out that we remember that v equals r omega, right? Where this is our linear and speed, and then this is our rotational speed, omega. So this is something noting. I don't even know if I taught you this earlier in the year, to be honest. If we look at this formula, the centripetal force is mv squared over r, or if again you don't like saying fc, putting f net. Know that they might reference that as a centripetal force. And I stick now that in for v. What do I get? I would have to square both of those, right? Mr squared omega squared over r. One r cancels with the other r on top. And what am I left with? Mr omega squared. So this means you can actually model the centripetal force as mr omega squared, or you can model it as mv squared over r. Those are both representative of the centripetal that's causing it to rotate. It's the extra net force in the forward direction. It's causing it to continue at a constant speed and constant radius. It can be in terms of omega. Here I'm expressing it as a function of omega up here. And here I'm expressing v. It depends on what they give you. If they gave you omega, and they might throw omega into this. They like multiple ideas and topics into one thing. You need to know that there's this connection here, right? That's on the equation sheet. This is not. Omega squared is not. I think only mv squared over r is. So be aware of that. And then, so it's worth noting that if you were referencing just the centripetal acceleration part in terms of omega, the centripetal force, as I've said, is mr omega squared. What we knew Fc is m times v. So that means the centripetal acceleration is actually r omega squared. So that means when we're writing centripetal acceleration in terms of v, normal per second speed v, and it's v squared over r. If we're writing the centripetal acceleration in terms of omega, rotational speed, radians per second speed, it's r omega squared. So there's two different variations of representations for centripetal force and centripetal acceleration. I've got them on the top and the bottom of the screen, right? When you're dealing with omega, we have r omega squared for the centripetal acceleration, or m, because as soon as you have an acceleration, you multiply it by m. Ma, that's a force. So r omega squared for a centripetal acceleration, if it's multiplied by m, like on the top, m r omega squared, then that's your centripetal force model. Or v squared over r is your centripetal acceleration in terms of v, you get it per second speed around the loop. If you multiply it by m, then you got a m times a scenario, that's a force, centripetal force, net force, mv squared over r. I won't mention, the other connection now. I mean, the other similar, formula to v equals r omega is a equals r alpha. But this represents a linear acceleration, and we wouldn't use this here because we're assuming that as the thing goes around the loop, it's moving the same distance each second. We're assuming that it's moving at a constant speed, meaning that the linear acceleration is 0, right? So that means if the linear acceleration is actually 0, then there is no rotational acceleration. There is a centripetal acceleration, check, which worth noting. There's 3 accelerations, right? There's your linear acceleration, which is due to the rate at which your speed, I should say, usually used to represent an increase in speed, delta v over delta t. There's a centripetal acceleration, which is used to represent the rate at which your direction of v changes. Technically, you can have both, but they don't ever give that to you. You could be going around a circle and speeding up, right? They don't give that to you. They give it to you in AP Physics C in college, where it's the overall magnitude of the acceleration. If you're going around a circle and speeding up, is the sum, the addition of A plus AC, vector-wise. But they don't do that to you guys. Just know that you have your normal acceleration in AP Physics 1, which is usually in relation to a rate at which your speed increases, or the centripetal acceleration, which is the rate at which the direction of v changes as you go around a circle. And then you have your rotational acceleration in radians per second gained as something's rotating around a circle. how much the rotational speed in radians per second increases each second, which is, again, alpha is in radians per second squared. So I'm just pointing out you wouldn't use that here because if you're going, if this is the discussion is constant speed motion around a circle, then A linear is 0, and therefore alpha is none of those are just okay. Then we're going to do one more example, and then I'm going to close this lesson out. The other example is the car. You guys did the car. This is now the rotary problem. You have your car going around. Remember the Pivot Lab? Watched your car driving around the rotary, literally a drone had taken a video of it, right? It's a car. This is the rotary car problem. Rotary / car problem. Top view, right? It's rotating around at a constant speed because that's all they're going to give you. They're only going to give you circular motion problems with constant speed. So as we reference this, if someone, let's say we're referencing it here, and someone said draw the free body diagram for that, well, we'd really have to take a side view again. It's hard to draw from the top view the free body diagram because you wouldn't be able to draw the gravity force vector, which goes into the page, and the normal force, which would come out of the page. So you'd really have to imagine, changing your view. Now you're looking this way. Now your car is on the side. Again, normal force up, gravity force is down. Those still cancel. What force is causing it to navigate this turn? What force is causing its direction of V to change? That's a frictional force. It's the static friction force. Remember that FK is sliding friction. That's why all you say, when I say FK, I say kinetic or sliding. And I always repeat or sliding so that students remember that a car because otherwise, if you just think that kinetic friction is just movement friction, then it just involves movement, then it would be easy for a student to think that a car that's driving, just the way wheels are really just turning, then that's kinetic friction. No, it's not. No. Kinetic friction is sliding friction. That's only when the car jams on its brakes and slides, or a box is sliding across the pavement or a floor. Kinetic. That's sliding kinetic friction, right? There might be friction in the wheels that are like providing some counter torque to the wheels, for example, that slow your car down. That's not what we're referencing here. So you got to be very careful to recognize that the force that is involved with this problem is a static friction force. FF, there should be a little F in there. FFF. So always pointed towards the center. It's the rule. Circular motion is always forces towards the center. What's the direction of the acceleration vector that the static friction force produces? It's toward the center because F and A are always in the same direction. That's what F equals MA means, because F and A are both vectors. They're proportional to each other. So AC is always in the same direction, right? So that's how we would draw the free body diagram on the bottom. We make sure that we understand that it's always pointing towards the center, that the force for cars and anything that's on a road comes from the static friction force, which means we have to remind ourselves that the static friction force is equal to the coefficient of static friction times the magnitude of the normal force. Talking magnitudes here, of course. This is on your equation sheet, yes. But remember our diagram for the car that we just looked at, which remember, these don't change. Anything sideways, just like the bowling ball, does not change these up and downs. If they're equal, because they have to be, because the car's not flying up into the air like a plane or sinking into the ground, it's just staying along the same horizontal plane, then any vertical forces, so Fn must be mg, right? Reminding you, this is your formula of the static friction force. So if the static friction force on the tires from the asphalt is equal to coefficient of static friction between the asphalt and the rubber tires, which is a textural thing, which you guys remember. And this is the weight, right? A percentage of the weight of the car, because mu, remember, mu s is usually between 0 and 1. Usually. There's some that are higher, but the vast majority of coefficients are less than 1. So if this is true, and we recognize that, the top-down view again, that the force pointing in is the frictional force. What's this? And oh wait, that's a centripetal force, and it's actually the only one, because when we looked at again our diagram, free body diagram, There's no other force, horizontal force. That means the net force, called the centripetal force, I guess, in this case, right, is equal to mv squared over r. And who is that? That's the static friction force. They're all one and the same. We're not talking here. We're talking one force referenced three ways. The static friction force is the net force. Again, these two canceled. And the centripetal force that's causing it to go around in a circle. So that force, we say the net, or this, if you again want to just write net, it's fine. Circular motion, the net force must be equal to mv squared over r. What is the net force? Again, cancel for Fn and mg. It's just the static force. Oh, we have an expression for that? Yeah, we do. USMG for the static friction force. Cancel by dividing out our m's, right? So what are we left with as a model for this? US times G equals the speed of the car as it zips around and round at a constant speed, remember? And R is the radius of the rotary. What are the typical questions they ask? They might give you information about V. They might give you the period, the time that it takes to go around, and you know the radius of the rotary, and you think, oh yeah, that's easy, I know that. So I can fold that information in to get V, right? They might give you, again, the speed. No, they won't. They'll probably give you the timing, the period, and the radius. You'd have to work out the speed V. And then they might say, based on this information, what is the coefficient of static friction between the road and the tires? That's what you did in the Pivot Lab earlier this year, right? And I guess you'd have to divide both sides by G, right? Just from this model, this is all that was left after the M's canceled away. And you'd get mu S equals V squared over RG. And you'd have to plug in the V, and you'd plug in the radius of the rotary, and you'd plug in G, but they're going to want 10. And boom, you get the coefficient. Or what's the only other thing they do? They give you the coefficient, and they say on a rainy day, the maximum coefficient of friction is actually only 0.4 or less than when it's a dry day. And if that's the case, what is the maximum speed that this car can drive at around this rotary? And if it goes any faster than that, the wheels will start to squeak and it might wipe out. Because remember, mu mg is a maximum amount of static friction force. So when you have, tires on the road, mu s doesn't change. If it's just 0.4 for that day, then it's 0.4 for that day. And the weight mg is the weight of your car, right? Which means the total amount of traction force you can get is a maximum at that. It's the most it can possibly provide. Yet what you ask for, what your tires ask for, depends on the speed of the car and the radius of the turn that you're going around, right? So if this gets capped, if the force that's being provided to you has a cap, it can't go higher than that. That means something in here is limited as well, right? And if they decide, well, it's a rotary and R just stays the same, then G doesn't change. Then what's the thing that's limited? V is limited. That means dependent on what mu mg is, V must have some maximum value, right? Because that's what we said in the beginning. Mu mg was equal to mv squared over r, right? So if they did that, which is the other way this problem goes, they ask you for what the maximum speed is. You'd say, again, mu s times m times g, that's static friction force, equals mv squared over r. Amazingly, again, it doesn't depend on the mass of the car. And this, as soon as you are doing this, you'd represent the V max, the maximum speed. And then if you multiply both sides by R, it looks like I get mu S times R times G. If I multiply both sides by R, right? And then I'd have V squared, V max squared equals mu RG, and then I'd have to square root it, or to the 1/2. So this would be the maximum speed going around the rotary. What does it depend on? The coefficient, sure. If it's a drier day, notice that the maximum speed you can go around the rotary is proportional to the square root of mu. More importantly, just proportionally to mu, which means on a drier day, should you be able to go faster around the rotary without wiping out? Yeah. What if on a rainy day, mu, the coefficient of friction diminishes, goes down? Well, maximum speed you can travel on that day goes down. Everybody knows that. A snowy and icy day for sure, mu is much less. Well, maximum speed you can take around that rotary on a snowy day should be much less. Otherwise, you're going to wipe out, right? And recognize that Vmax is also proportional to R. Vmax is proportional to the square root of R. So that means if you decide to take a much wider turn, you don't have to worry about hitting your brakes. Right? If you had two choices, you're on a road and you can either take this turn or you can take a much wider turn. The second one is a much larger circle. Remember, these are circles that you could put in here. This other one would be a massive circle. So if you're coming off this rotary or something at 50 miles per hour, which one do you definitely have to potentially slow down on, path A or path B? We all know path B, oh, it's a sharp turn, slow down, right? Well, that's because of this, right? Because if R, this has a smaller R, the other one is a massive R. So the smaller radius the circle is, or the curvature of the radius of that curvature, when it's smaller, R goes down, speed that maximum speed you can have safely, it goes down. I just remembered one other thing, and then I'm going to end, that I never mentioned the static friction force on the inclined plane, which I should have. So remember that, because I was just talking about static friction, it just popped into my head like, oh yeah, I never talked about that. In the simplest case, when something is just at rest on frictional surface, I mean, someone just places it there and it just doesn't move all by itself. Well, because the frictional force, the static friction force, is equal to mg sine theta. If it's all by itself and it's just sitting all by itself, and nobody's touching, no ropes, no nothing, just got enough friction on there to make it so that works, right? If the angle increases, remember that the maximum static friction force is the mu s times Fn. The maximum amount. When you're talking static friction force, the maximum amount that you can get, and after that it just slips and it gives up. Can't provide anymore. Remembering that on a inclined plane, n is actually the opposite of this one. Fn going up is actually equal to mg cos theta, right? So the maximum static friction force is mu s times mg cos theta, right? So in the critical angle, which you might remember when you raise it up, and it's just about to slip, and oh, there it slips. Okay, back down the angle just a little bit. Okay, put it back. All right, it doesn't move. I know if I go a little more of an angle, then static friction force can't go any higher because it's a maximum amount. So the moment I go a little higher on the angle, mg sine theta gets a little bit longer, and the other one doesn't. Now I've got a net force in the downward direction. It starts to slide in the downward direction and accelerate, right? But usually what they're referencing is the critical angle. When it's just right at that maximum angle, you can actually do an experiment to work out what the coefficient of static friction is. So I wanted to bring that up right now. Right at that position, again, just going to write down what I just had. The maximum static friction force on an incline is, because this is Fn again. And we know that the gravity force, Fgx, pulling it down is mg sine theta, right? And again, like I said, in our picture, mg sine theta must be equal to the upward static friction force, which we're modeling with mu s mg cos theta. It must be equal, right? So you would say, okay, at an equilibrium, static equilibrium is what it's called, the maximum static friction force at this is called the critical angle, theta c. The maximum static friction force, which is up, equal to the Fgx pulling down. Then when you re-express them, mu s mg cos theta equals mg sine theta. The mg's cancel. And then when you divide cosine over to the other side, you end up with sine theta over cosine theta, which is actually equal to tan theta. And that theta is theta c, which is the critical angle. It means any angle over that, based on this coefficient of friction, if you go up any angle higher than whatever theta c might be, it might come out as 37 degrees for a real experiment, right? If so, I just point out that is the result. People use this to determine the coefficient tan of theta c. So They do the experiment. They find out what the critical angle is. And they measure it. Oh, it's 37 degrees. All right, put tan of 37 into a calculator, hit enter. If 0.41 comes out, that means the coefficient of static friction is 0.41. That's how they do that, right? And the opposite could be true, where if you know the coefficient of static friction, could you technically predict the critical angle? The coefficient of friction is now the static friction coefficient between the ramp and the block. Could you technically predict, if you knew that coefficient, predict exactly the angle that it should, oh, there it goes, it's going to slip, assuming that you slowly raised up the angle? Yeah. How would you do that? Inverse tan, right? So inverse tan, arctan of mu s equals theta c. This is a very specific problem. Like, you may or may not get it on, but it's specific to that whole incline. But if, God forbid, it came up on a full response, free response question, 20% of your test. And it has. This is an experimental problem that has come up in the past. So there's that reminder. All right. I think I covered everything I wanted to do for this introductory motion lesson, plus this little one that I forgot about from before. I did the centripetal acceleration, centripetal force, recognizing the two vectors that point towards the center of the circle. I did the problem. I did the car problem. Talked about what they usually ask. I think I'm good. So in the next lesson, I'm continuing to move forward with the circular motion, but now we're talking about the vertical plane, motion along the vertical plane, which is like the swinging bucket that goes around, or the Ferris wheel that goes around, or the loop-de-loop, or a car coming down a hill and it goes over a bump, and you have to talk about the normal force on the car as it goes over the bump. Those are all circular motion vertical along the vertical plane. Today's discussion was circular motion along the horizontal plane, right? The other ones can be even more challenging. So that's what we're going to tackle in the next lesson. In addition to those, in the next lesson, I will be talking about gravity, gravitation, Newton's laws of gravitation, some stuff about orbits, some stuff about energy, potential energy. As much as I can in the next lesson. I don't know if I'll be able to squeeze in Kepler's laws. I'll try. Following lesson, beyond that, I'll do a laws, and then not the next lesson. In the lesson after that, I would do a quick lesson on Kepler's laws, and I'm hoping to just squeeze 30 minutes, squeeze in momentum within 30 minutes, and then literally be done. Be done with my review. At least I'll probably still do a rotational review, but as I said in my post, that's going to be optional for you guys to watch. It was pretty recent. So I think these ones were more important since it's been such a long time since you've seen them. But I will optionally, for those students, have that option of watching any that you might want to watch, torque, all that sort of stuff, moment of inertia, rotational kinematics, and then simple harmonic spring mass spring system. Because I'm not going to think of it later, so I'm going to say it. I'm going to do it real quick. Just remind you, that the Hooke's law, right, should have been done earlier. When you stretch out you stretch out a spring, then there's some distance delta x that you stretch it, or you can compress it. Lax length. You have the x equals 0 mark. That's not supposed to be an alpha. Right, and then you could reference, some change in its length, either a compression like on the bottom or a stretch on the top. You remember doing this slab, right? This is called Hooke's law, and each time if this was me pushing it over here on the bottom, I'd have to push it in with my hand, which means the spring would have to push back on this. Force would be back that way. It's trying to spring itself forward back to where its normal length is, right? On the other hand, if it was me pulling on this side, F me, this was F me down here, then it's going to do Newton's third law, because nothing can ever avoid that, and it's going to try to pull back on itself, right? So it always applies a force in the opposite direction to the direction you're pulling it or pushing it. You push it in, it pushes out on you. You pull it out, it pulls in on itself and you, right? And you did this, and you discovered that the force increased with greater and greater stretches. Just need to know that it works also if we had done a lab which was compressing it the same. And then we found out there's no force again when there's no stretch or compression. And then in this one lab, we were just further and further. You saw that it was linear, right? We plotted that out as the spring force versus delta x, called the elongation. And then we talked about the idea that for different springs, the slopes of these graphs might be different. Some, for some delta x, if this was like, 1 centimeter, for what, for each of these represent two different springs again. Let's say spring 1 and spring 2. For spring 1, if I stretch out spring 1 at whatever I said, 1 centimeter, that generates some amount of force. Maybe it's 5 newtons. It's supposed to be 5. On the other hand, the same 1 centimeter for spring 2, that generates, 10 newtons, right? So that means spring number 2 has the higher spring constant, right? Because it took 10 newtons of force just to compress it by 1 centimeter, where for spring number 1, the one I have on the lower one, generated only 5 newtons, or required only 5 newtons of force to stretch at the same 1 centimeter, right? And that's the concept of the spring constant, right? It's a strength profile for a particular spring, right? How do they typically, provide questions? They could say there's a spring like this sitting here, and then we put something heavy on it, and it compresses like this. And they tell you what that compression is. Well, based just on this information, m and delta x, what is the spring constant? Well, this thing is in equilibrium now. This ball, mg is pulling it down. The spring force is pulling it up, pushing it up. They're equal to each other. So it's Fs equals mg. Since this was linear again, right? Hooke's law is k delta x. That is the spring force. It's mx plus b. The plus b is 0. So this is in the form of mx plus b because it's linear, right? And that's the slope, right? Let's point that out. When we looked at the graph below, sorry, it's not right. Delta f over delta x. That is the slope, right over run, k equals delta f over delta x. And when you just multiply both sides by delta x, you get f equals k delta x. That is Hooke's law, right? Solving this for k, they said based just on this information, what is the spring constant? This is the idea here. You'd say, okay, k is equal to the amount of force is being applied to it in this equilibrium position here, divided by how far that it caused it to stretch. Or they just tell you how much force was applied sideways to it and how much is stretched. Or they hang it from the ceiling. They say we hang a mass from the ceiling, and they tell you the mass and it stretches by some amount. How do we figure out what its spring constant is? Same idea. Because even if this thing was hanging downward, here it normally is, and then they stretch something like this, and they give you this. Well, same idea. When it's in the stretched from the ceiling position, this is kind of like that. This would still be mg down and an equal amount of force fs up because it's not moving, it's just sitting there. And it would be the same thing I did over here. Everything I had done on the top right of the screen over here is exactly the same. Right? You'd still say mg is equal to k delta x because the spring force is x. K is whatever the weight of it is divided by delta x. Right? And recognize there's an inverse proportion between delta x and k. So that means springs that have small compressions when you push them with a certain force have large k, or the opposite. When you apply the same whatever amount of force, if it creates straight change in its length, delta x, that means k is actually small. It's weak. It's a weak spring, right? And k is also proportional to mg. Well, although that actually, that's not even worth saying. To be honest, I think if we have k is mg over delta x, I'd say it would be more sensible to make the comment that delta x, k delta x is equal to mg, right? That delta x is proportional to m, to weight. That's more sensible. Meaning if you hang twice as much weight on this thing that's hanging from the ceiling, then we would expect delta x to double. Or if we put 3 times as much weight on it and let it go down and then just rest on its own in its new equilibrium position, it'll be 3 times lower than before, right? All right, that's Hooke's law. So I was, because I just popped into my head since I was saying we're going to be doing rotation in SHM, mass spring system. I was like, wait a minute, that the Hooke's law technically falls into the dynamics unit, right? Hooke's law, and then it gets brought forward again later in simple harmonic motion because it's a mass spring system, right? So check, done with that. Again, next unit, next video will be quick on Kepler's laws, and then hoping to do 30 to 35 minutes on energy, 30 to 35 minutes on momentum. Then everything from that point forward will be optional. The next video from that will be rotation, rotational inertia, rotational kinematics, and then maybe one last one on simple harmonic motion, mass spring system. But I might just actually just first email everybody or just ask you, does anybody even want it? Because it was just very recent. If nobody says they really want it, then I might just stop at that. All right, guys, I'm getting there. I'm giving you my all. I'll tell you, I'm giving you my all. My first video was starting to record at 5:45 a.m. this morning, and it's Saturday morning. So I'm giving you my all. I hope you guys are giving me your all. And if you're hearing this and listening to this, then that means you are. And I'm very, very appreciative of that, because when we work hard on something, we want to see it pay off as much as possible for those people that you're trying to, obviously, right? So I know that you guys are doing your best. So keep going. We're almost there. All right. I guess I end the same way every time. You guys know what I'm going to say? See you soon.